All available experts, please report to room A9.
Hello guys, KTaNE here, and welcome to integer trees. So this is what the module will look like. If you remember, this module used to look a lot different, but it's recently been revamped, and this is what the new version looks like. And the aim of the module is slightly different. So we're going to be given two numbers, which we call P and Q, and we're going to be building two integer trees out of them. So, how do we do that? The tree structure for P corresponds to the first character in the serial number in the table below. First character is P, so our structure is going to be this, where the white points are where we can put numbers, the black points we can ignore. So our first structure will be this and this. The first three rows will always be all clear, but then the bottom part will be the interesting part. So we have nothing, nothing, something, nothing, nothing, something, something, nothing. And now we can do the same thing for the bottom number as well, because it's going to be the same thing, just with the second character of the serial number for the structure, which is I. So in this case, these rows are going to be the same. And then nothing, something, nothing, 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 something, something, nothing. And we're now going to fill this in with sort of the maximum factors going down for each of these numbers. If you don't get what that means, we're just effectively going to find the largest single digit number, n, which divides evenly into P, or Q.
Emergency cleared. All personnel, please return to your stations.
So, basically we prioritise 9 over A, 8 over 7, and so on. So, our first number is 7381125. As you can see here, the number can be as big as in the millions, or as small as in the hundreds. So, let's start off with 9. 9 does divide into this, so we can put this at the top of this one. Can it be divisible by 9 again? Yes. So you can put, we then move to the next available spot and put a 9 in there again, and we keep on doing it over and over again until we get down to 1, which we don't just ignore, we just put 1s in everything else basically. So is it divided by 9 again? Yes. Again? Yes. Again? Fun enough, yes again. But I don't think it'll be a yes again. Yeah, so divide by 8? No. 7, 6. Next one it can be divided by is 5, so we put it here. And we can see that it's divided by 5 again. As soon as you go down numbers, as soon as you go past a number, you don't have to go back to it because it would have been divisible earlier otherwise. So meaning, if it's not divisible by 5 again, we don't have to consider 5 upwards. We can see here, we can divide by 5 again. And now we've got to 1, so these two are going to be 1. And for the concept of this module, anywhere we put x's are actually going to be zeros. Just to make it clearer. So let's do this again with the bottom number, which is 147. Meaning I think we're going to hit 1 quite quickly. 9, no. 8, no. 7 is our first one. 7 is going to be again. And then 3. And everything else is going to be 1. Because the biggest number that goes into 3 is 3. Biggest single digit number, and then that will leave us at 1s for all the rest of them. And then everything else will be zeros. So what do we do with these? We're now going to make a third tree by taking the absolute difference between each corresponding node, including the blacked out ones being zeros, hence why I changed them to zeros. So we have 9 and 7, which is 2. 9 and 7, which is 2. 9 and 3, which is 6. Yeah, 9 and 3, which is going to be 6. 9 and 1 is 8. 9 and 1 is 8. 5 and 1 is 4. 5 and 1 is 4. 0 and 0 is 0. 0 and 1 is 1. 5 and 0 is 5. 0 and 0 is 0. 0 0 is 0. 1 1 0. 1 1 0 0 0. So, what do we do with this? We are first going to multiply every non-zero number with each other. So that is going to be 2 times 2 times 6 times 8 times 8 times 2 2 6 8 8 4 4 and 5 2 2 6 8 8 4 4 5, and then we're also going to multiply by the positions here. So let's quickly switch these back to x's. We're going to find any column in these two input trees which both had x's to begin with. So that's 1, 2, 3, 4. 4 of them match between them, so we're going to multiply this by 4. And this is the number we're going to be inputting. So that's going to be 2, 5, 1, 9 here, and 4 here. So our inputs could be 491,520, and if we got it right, we get ourselves a module. The numbers aren't always going to be this big. It's probably just because we had such a big difference between these two numbers. We've got a big number here. But it could easily be as small as 48. So let's do another example. So, our trees are actually going to be the same again, because we have the same zero number. But this will apply to any pair of these trees. Basically, the only thing that we know is going to stay the same is 4 is going to be our extra factor here. But say we had, let's take 0 and 1 here. If we had these two, the ones that would match between them are just these last ones. So this would also be 4. Because, sure, there's two extra ones here, but they don't match between them. And let's take 0 and O. Don't match, don't match. Match here. Yeah, there's a match here, and 2 matches at the end, meaning that this one would be multiplied by 3 rather than 4. Anyway, going back to our trees. Let's create our trees again. So our number is 102, 4000. Did it divide by 9? No. Did it divide by 8? Yes. Did it divide by 8 again? Yes. Did it divide by 8 again? Yes. And again. Again? No. 7, 6, 5. Divide by 5 now. We divide by 5 again. And one more time. This is divisible by 2. And then the rest will be 1s. Now, using the other number, 117600, we're going to have 9, 8, 8 again. Not 8 again. 7 is though. 7 again, yes. doubt it's going to be 7 again, though. Yep. 6s, though. Not 6 again, so 5. That's going to be 5 again. And then 2 again. And then 1, 1, 1. So we can just double check this by multiplying all the non-1 digits. So we've got 8 times 8 times 8 times 8 times 5 times 5 times 5 times 2, we get the top number. And 8, 7, 7, 6, 5, 5, 2, we get the bottom number. So again, we're now going to take the absolute difference between each corresponding node. 8 and 8, 0. 8 and 7, 1. 8 and 7, 1. 8 and 6, 2. 5 and 5, 0. 5 and 5, 0. 5 and 2, 3. 0, 0, 0. 0 and 1 is 1. 2 and 0 is 2. 0, 0, 0. 0, 0, 0. 1, 1, 0. 1, 1, 0. 0, 0, 0. So as you can see here, this number is not going to be as big as our previous number because they're only non-zero numbers. Non-zero and non-1 numbers are 2, 3, and 2. And then, of course, we had to do what we did last time. 1, 2, 3, 4 matches of empty spaces. You only count the empty spaces. So we multiply by 4. So our final number is 48. Full enough to the number I think I mentioned. And if we got this right, we get another submodule. So that was integer trees, or should I say the new integer trees, compared to the old one. It's possibly slightly longer than the original one, but still relatively simple to understand once you've got it down. So hopefully this tutorial made integer trees a bit more clearer, and I'll see you guys in the next tutorial. I'll see you later.